Okay, so we have a little bit of a digression here, but not really a full digression because understanding and having a comfort level with our empirical result, our x equals a cosine omega t. Now, I didn't put a phase shift in here, and I'll explain the phase shift more in our next lesson. But basically, if you start the oscillation off, as we did in our last page of notes, let me just very quickly go to that. If you start it off, as we did here, where we are taking time t equals 0, at x equals positive a, that will always correspond to no phase shift. So the cosine function is starting where a cosine function should start. So we don't introduce a phase shift unless we are forced to, and I'll talk more about the phase shift in our next lesson as well. But in terms of understanding how it is this angular speed omega gets introduced into a system that is 100% linear, there's no angular motion to the block on an end of a spring oscillating back and forth on a horizontal linear plane. Well, when we say that the angular motion maps onto this linear motion, we mean it in a very literal sense, meaning the angular motion, see the analogy down here, how the mapping occurs. The angular motion of this wheel maps or projects onto the linear motion as a perfect match. So, to me, this is a great example of seeing why it's important to study physics and math together, because physically, we're talking about a projection or a mapping of one quantity onto another quantity. And in math, you can learn it with just the words, but without seeing physically how this projection and this mapping occurs, I think it's very difficult to get the same level of understanding. So what we have here is our block is pulled down, and we're saying that's position, maximum amplitude, and positive. So we're taking a little liberty with the down being positive, but we're saying we pull it down, that's at position 0, that's positive. We release it, it will have its maximum speed as it passes through its equilibrium, it's x equals 0, and I have down here that we have to be a little careful when we have a vertical block hanging from a spring. It still undergoes simple harmonic motion, but the equilibrium is given here. So here I have x equilibrium, so make sure you get this down into your notes. That the equilibrium position, we wouldn't use x equals 0 because the spring would start at a natural stretch position, and we studied this when we did springs as well. But getting back to the mapping, the projection, if we looked at the shadow of the peg on the screen, so that project or that map onto the screen, it will match perfectly the motion of the block if that wheel is rotating with this omega. So please put that arrow into your notes. Make sure you have that omega going with this wheel. So there is the mathematical projection or mathematical mapping. Mathematicians will use that language when they are using an analogy like this from one type of variable to another. If the mathematics describes of one will describe the other, in this case the rotational motion describing the linear motion. So again, a little bit of a digression, because we could have just continued to use the equation without seeing this or discussing this, but I think it's a really powerful way to see how mathematics is used in two different realms.